We often talk about the vastness of the universe, about its immense size, but how often do we stop to truly ponder its shape? Not just how far it stretches, but how it exists geometrically. It's a concept that defies our everyday intuition. You see, we are used to boundaries, a table has edges, a room has walls, even a planet has a surface. But when you begin to contemplate the cosmos as a whole, the very fabric of space itself, those familiar rules seem to vanish. Cosmologists have wrestled with this for decades. Is the universe truly infinite, stretching forever? Or is it finite? And if it's finite, where does it end? What lies beyond that edge? But perhaps that's the wrong question entirely. The mathematics suggests something far more intricate, something exquisitely difficult to picture, yet breathtaking in its implication. Imagine the universe is finite, yes, but without any edges, no borders, no true boundaries. It sounds contradictory, doesn't it? A closed space that never ends, but it's not. Not if we consider geometry in higher dimensions. Think of the surface of a sphere like our Earth. If you start walking in a straight line, always forward, you will eventually return precisely to where you began. You've completed a loop, a grand journey, yet you never encountered a wall, never found an edge to fall off. You simply kept going. The Earth's surface is a two-dimensional space curved within our three dimensions. Now stretch your mind further. Imagine something akin to that, but for space itself. A three-dimensional space that is curved within four dimensions. This is what some leading models of the universe propose, a kind of 3D surface of a 4D sphere. In principle, you could journey in a straight line through the cosmos forever, and never reach an end, never fall off into some void. Space would simply loop back on itself, a magnificent self-contained infinity. It's a profound redefinition of boundless. Isn't it? Our very notion of outside evaporates. And the strange thing is, when we gaze out into the universe using our most powerful telescopes and satellites, observing the cosmic microwave background, the faint echo of the Big Bang, we don't see any obvious edge. There's nothing that screams, here's the end. Instead, the cosmos appears remarkably smooth, homogeneous on the larger scales. This smoothness, this apparent lack of dramatic curvature, has led some to suggest that perhaps the universe is flat, meaning it could extend infinitely. Yet even this perceived flatness can be deceiving. A sphere vast enough appears flat if you're standing on a tiny, insignificant speck of it, much like standing on a beach and struggling to discern the Earth's gentle curve. The curvature might simply be on a scale so immense that our instruments for now cannot fully perceive it. Even if the universe is indeed curved, closed and finite, there would still be no discernible centre, no absolute middle where the Big Bang occurred. Because it didn't happen in space. It was the happening of space unfolding and expanding everywhere simultaneously. There was no outside for it to expand into just more of space stretching into itself. So you don't need an edge, you don't even need an outside. It's just space ceaselessly unfolding. The idea that you could travel forever without reaching a wall, a barrier, is not just strange. It carries a deep, almost spiritual beauty, a sense of infinite possibility, woven into the very fabric of existence. It makes you wonder how much our intuitive grasp of reality is merely a reflection of our limited perspective. There's this other profound truth, something I heard long ago that has resonated within me ever since everything in your body and our bodies was once part of a star. Not as a poetic flourish, not a gentle metaphor, but as a literal, undeniable scientific fact. This isn't science fiction, it's the very bedrock of physics and astrophysics. Consider the elements that compose you. The carbon, forming the intricate structures of your skin, the calcium giving strength to your bones, the iron coursing through your blood carrying life. None of these existed at the very beginning of the universe. In that primal dawn, there was only hydrogen and a whisper of helium, the simplest, most fundamental elements. All the rest, all the complex, heavier atoms, had to be made forged in cosmic crucibles. And those crucibles were stars. The process is called nuclear fusion. It is the very engine that powers our sun and every other star blazing in the night sky. It's an extraordinary feat of cosmic alchemy. These massive glowing spheres of gas under immense gravitational pressure and unimaginable temperatures take hydrogen atoms and squeeze them together until they fuse, becoming helium. As stars age, they push this process further, fusing helium into carbon, then carbon into oxygen, nitrogen, silicon, continuing all the way up the periodic table to iron. But iron for a star is a limit. It acts like an unyielding wall in stellar physics because fusing iron no longer releases energy, it consumes it. Once a star's core accumulates enough iron, it loses its ability to sustain itself against the crushing force of gravity. The star's delicate balance is shattered, and it collapses inward. This catastrophic implosion leads to one of the most violent and spectacular events in the universe, a supernova. And it is here in this cataclysmic final breath that the real magic happens. In those fleeting fractions of a second as the star dies, conditions become so extreme, temperatures so high, pressure so immense, that atoms smash into each other in ways never possible before. Suddenly elements like gold, uranium, platinum, copper, all the heavy elements that couldn't be forged inside a normal star, are created in the ferocious heart of the explosion. These newly minted elements are then flung outward, hurled across the vastness of space by powerful shock waves, drifting into the cold, desolate regions between the stars. Dust debris, scattered atoms, they wander for millions, even billions of years, until by some gravitational whisper some of that material begins to gather once more. Clouds of it slowly collapse under gravity's patient hand, forming new generations of stars, new planets. And sometimes, like here on this pale blue dot, they form worlds where the intricate dance of chemistry evolves into biology, where atoms organize themselves into living systems, into eyes that see, hands that grasp, and minds that ponder. So when you draw a breath right now, the oxygen filling your lungs was once inside a star. The calcium strengthening your teeth, the very same cosmic origin. You're in the most literal sense imaginable stardust. You walk around every day carrying the ancient remnants of celestial bodies within you, a living testament to cosmic recycling. When you truly grasp this, it doesn't just alter your perspective, it reshapes how you perceive yourself. You're not merely here now. You're a continuation, an unbroken thread in processes that began billions of years ago. You're the universe itself, slowly, magnificently becoming aware of itself, arising through an extraordinary chain of explosions, collisions, chance events, and the relentless march of time. You're not separate from the cosmos. You're the cosmos arranged into something that can think, something that can ask where it came from. This isn't just poetic license. This is fundamental physics beautifully rendered. It's a humbling thought, a quiet reminder of our profound interconnectedness with everything. There's something truly peculiar about time. We live within its relentless flow. We measure it with incredible precision. We age under its steady march. Yet the deeper you delve into its nature, the more you realize it's not the fixed, absolute, universal constant we intuitively believe it to be. This is one of the profound revelations that emerge from Einstein's work. Time isn't a universal clock ticking uniformly for everyone everywhere. Instead, it's intricately woven into the very fabric of the universe, a cosmic tapestry known as space-time. And this fabric, this time, can stretch and bend depending on how you move through space or where you are in the universe. The idea, now rigorously tested and no longer mere theory, is that if you're moving at extremely high speeds approaching the speed of light, time for you actually slows down. From your subjective perspective, everything feels perfectly normal. Your heart beats at its usual pace, your thoughts unfold as they always do. But for an external observer watching you from a stationary position, your clock would appear to tick slower. This phenomenon is called time dilation. It's not just hypothetical. We've proven this with atomic clocks, the most accurate timekeepers we possess. Take one atomic clock and place it on a fast-moving jet, leaving its twin on the ground. Upon the plane's return, the clocks are no longer in sync. The one that travelled has ticked fewer times. Time truly, physically, objectively passed at a different rate for that moving clock. Then there's gravity. The other critical piece of this cosmic puzzle. Massive objects like our Earth, or even more dramatically a black hole, warp the very fabric of space-time around them. It's like placing a heavy bowling ball onto a stretched rubber sheet. It creates a curve, a depression affecting everything nearby. And time too follows these curves. So if you're closer to something massive, time literally runs slower for you. It's not just a perception, it is a physical reality. A clock nestled near the Earth's surface ticks marginally slower than one orbiting high above in space. The difference is minuscule, measured in nanoseconds, but it is unequivocally there. We must account for these subtle shifts. GPS satellites, for instance, rely on extremely precise timing to pinpoint locations. Without constant corrections for both their speed and their position within Earth's gravitational field, their timing would drift. You'd find yourself hopelessly lost in your own city as the entire system would fall out of sync. This means that right now, every single person on Earth is experiencing time at a subtly different rate. Every mountaintop, every airplane, every city at sea level, they're all ticking to slightly different cosmic rhythms. The differences are impossibly tiny, but they are real. No two people have ever lived the exact same second. You and I, our lives are offset by mere nanoseconds perhaps, but it is your personal time, your unique temporal experience. And that when you truly contemplate it is profoundly humbling, isn't it? We conceive of time as a universal inexorable flow, a shared river marching ever forward. But it is not. It is fluid, dependent on your location, your velocity, your proximity to cosmic giants. In a very literal sense, you are living within your own timeline, your own personal rhythm, dictated by the geometry of the cosmos around you. And no one else, absolutely no one else, is precisely in the same slice of space-time as you are. It makes our shared now a beautiful cooperative illusion. One of the strangest things, and I mean fundamentally properly strange, not just surprising but deeply odd, is the revelation that empty space isn't actually empty. That the vacuum, the vast silent void, isn't nothing. We grow up logically thinking of nothingness as simply that, a lack of anything. Remove all matter, all air, all light, all radiation from a room, and what's left you'd expect is silent stillness, absolute void. But quantum mechanics, the physics of the very small, emphatically tells us otherwise. It posits that there is something there always, eternally. When you descend to the unimaginably tiny scales, the Planck scales the very fabric of existence, you find that even where there are no particles, no energy that we can directly measure, the quantum field itself persists. And that field is perpetually restlessly fluctuating. It's as if space isn't a smooth, passive stage upon which events unfold, but rather a turbulent sea, bubbling and twitching with unseen activity, even when our senses perceive only emptiness. These are called virtual particles. They spontaneously pop into existence, appearing as fleeting pairs of particle and antiparticle, only to annihilate each other and vanish again, all within an infinitesimal fraction of a second. This happens so quickly, so ephemerally, that we cannot directly capture them. Yet their effects, their subtle ghostly presence, are very real and measurable. One of the most compelling pieces of evidence is something known as the Casimir effect. If you take two uncharged, perfectly flat metal plates and place them extremely close together in a vacuum, a truly empty space, a peculiar phenomenon occurs. They will actually move towards each other. Nothing is pushing them from the outside, there's no external force at play, it's the vacuum itself. The quantum fluctuations between the plates are slightly different from the fluctuations outside them, and this imbalance creates a tiny yet real physical pressure pushing the plates together. Pressure from what we perceive as empty space. And that is deeply, profoundly weird because it suggests that nothingness possesses energy. That even the lowest possible energy state, the fundamental ground state of space, still harbours this residual inherent activity. This isn't just a curiosity. Some leading theories suggest that this so-called vacuum energy may have played a monumental role in the very birth of the universe. In the period of cosmic inflation, that fleeting moment just after the Big Bang, when space expanded faster than the speed of light, it's believed that these vacuum fluctuations were magnified by the rapid expansion, seeding the very structure of the cosmos. Every galaxy, every star, perhaps even you and I, could ultimately trace our origins back to tiny ripples in the quantum vacuum. It grows even stranger because there's this elusive term in Einstein's equations, the cosmological constant, and it seems to be intimately connected to this vacuum energy. The universe is not just expanding, its expansion is accelerating. Something is actively pushing it apart, seemingly defying gravity. Our best hypothesis, still I guess to be honest, is that the vacuum itself, the intrinsic energy of space, acts like a kind of anti-gravity, not in a science fiction sense, but as a repulsive force causing space to stretch more and more rapidly. So the void isn't empty, it's more akin to a restless invisible sea teeming with temporary particles and latent energy, a quantum foam underlying all reality. The more we probe, the more we zoom in on what we thought was nothing, the more structure and activity we discover. It's a universe far more alive, far more enigmatic, even in its quietest corners than we ever dared to imagine. There's a fact not widely discussed outside of scientific circles, but once you truly absorb it, once you allow it to settle within your understanding, it radically transforms how you think about yourself. It's this: you are not just one thing. You're not a single, neat, unified organism. You're in a very real and biological sense a walking ecosystem, a bustling colony. You look in the mirror and see a person, a singular identity. But biologically speaking, you are more microbe than human. Literally. Your body contains approximately 30 trillion human cells, give or take. An enormous number, of course. But here's the astonishing part: you're simultaneously carrying around about 40 trillion microbes. Bacteria, viruses, fungi, and other microscopic life forms, with bacteria making up the vast majority. And they are everywhere, on your skin, in your mouth, but most densely, most riotously in your gut. Your digestive tract is where the true crowd resides, a veritable rainforest of microscopic life. Thousands of species, each performing its unique function, digesting complex fibers we couldn't break down alone, synthesizing essential vitamins, sending intricate chemical signals throughout your body. And it's not just that they are there, they are utterly, absolutely necessary for your proper functioning. Without them, you cannot digest certain foods, you cannot produce vital nutrients, and your immune system would fail to develop correctly. These microscopic organisms, many of whom have co-evolved with us over millions of years, help train our immune responses, guide inflammation, and astonishingly even influence our mood. This isn't metaphorical. We are uncovering more and more profound connections between our gut bacteria and our brain, a communication superhighway known as the gut-brain axis. It turns out that the bacteria thriving in your intestines can affect the production of neurotransmitters like serotonin. Some even produce it themselves. Imagine that your mood, your very state of mind, partly shaped by the invisible inhabitants of your colon. This makes it incredibly difficult to define precisely where you end and they begin. If you rely on them for survival, if they influence your behaviour, your health, even subtle decisions, are they merely passengers, or are they an integral part of who you are? That clear line between self and other begins to beautifully, inextricably blur. And what's even more fascinating is that every person's internal colony is unique, as distinct as a fingerprint. Your microbiome, the collective genome of all those microbes, is shaped by where and how you were born, whether you were breastfed, what you've eaten throughout your life, where you've lived, and even the people you live with now. We have only just begun to map this intricate personalised ecosystem. There are orders of magnitude more microbial genes in your body than human ones, thousands upon thousands more. The genetic diversity humming within you isn't strictly yours, but it collaborates with you, or occasionally works against you if the delicate balance is disrupted. And that's the other crucial aspect: this internal balance is extraordinarily delicate. When it shifts, perhaps due to antibiotics, changes in diet or stress, things can rapidly go awry. Conditions like irritable bowel syndrome, IBS allergies, Even autoimmune disorders are increasingly linked to disruptions within this microbial community. So you are not simply you. You are a host, a habitat, a planet, in a way populated by billions of organisms that for the most part diligently work to keep you alive and thriving. They are not mere passengers, they are residents, partners in the grand project of your existence. Once you truly grasp this, it's hard to feel the same way about your body or about what it truly means to be human. It's a testament to the profound interconnectedness of life on every scale. There's this thing I read once, and at first it sounded like pure fantasy, something ripped from the pages of a fantastical science fiction novel, too odd, too unbelievable to be true. But it is true, completely true, and it challenges our very notion of what constitutes life on Earth. The largest living organism on our planet isn't a colossal whale, nor an ancient redwood, nor any creature we typically imagine. It is a fungus, a humble, sprawling fungus. And the truly bizarre part, the part that makes your mind reel, is that you can't even see it. You could walk right over it, live your entire life near it, and never even know it was there. It's called Armillaria ostoyi, and it grows, or rather spreads, beneath the surface of a forest in Oregon, somewhere in the Blue Mountains. We're not talking about a few mushrooms poking up from the ground. Those are just the fruiting bodies, the visible tip of an unimaginably vast iceberg. Beneath the soil, there's this colossal network of thread-like structures called mycelium. It's like a biological web, an intricate underground nervous system stretching across nearly 9 square kilometres, that's 9 square kilometres, of a single genetically identical organism. Not a group, not a colony of separate individuals, but one unified being. And it has been there for an unfathomable span of time. At least 2,000 years, some estimates suggest it could be over 8,000 years old. Imagine that alive, slowly expanding its silent dominion beneath the earth. Before the Roman Empire, before the pyramids were even constructed, it has persisted through millennia, quietly growing unhurried, demanding no attention, simply performing its fungal duties, decomposing, absorbing, connecting. Because that's the other crucial aspect, fungi aren't passive recyclers. This colossal organism is an integral part of the forest's structure. Its mycelial network connects with the roots of countless trees, forming intricate partnerships. It sends signals, chemical messages between different plants, acting as a kind of wood-wide web. Forests, especially ancient ones, are now understood to communicate with each other through these vast fungal networks, not in words, of course, but through a complex chemistry of warnings, nutrient sharing and information exchange, all flowing through this hidden underground mesh. So this immense organism isn't just big, it's profoundly functional, actively shaping the entire environment above it, an unseen orchestrator of the forest's health and vitality. And we for the longest time didn't even know it was there. That's the detail that truly captivates me. For centuries, perhaps millennia, human beings walked over this land, felled trees, built settlements, and never once realized that a single living being the size of a small city lay quietly beneath their feet. It's like if one tree's roots stretched across an entire metropolis and it was still the same tree. It makes you wonder how much else is hidden from our perception. Not because it's infinitesimally small, but because it's vast and silent, because it doesn't clamour for our attention. We are so accustomed to associating scale with dramatic overt phenomena, volcanoes erupting, planets orbiting, storms raging. But this is a silent, profound kind of vastness, a living presence woven seamlessly into the very fabric of the forest floor. And it is still there right now, expanding millimetre by slow millimetre in the dark, a gentle, patient giant. It's a quiet reminder that the most extraordinary wonders often reside just beneath the surface of the obvious, patiently waiting to be discovered. There's something almost ghostly, something beautifully ethereal about this idea, that your body right now, even as you sit perfectly still, is glowing. Not in a metaphorical sense, not some poetic inner light, but with actual photons, actual real light particles. Your body emits light. Of course you don't perceive it with your naked eyes. It's incredibly faint, approximately 1,000 times weaker than the absolute minimum your eyes can detect. But it is there, constantly an unbroken soft emission. And it's not just you, it's every single living human being gently luminous in the profound darkness. This phenomenon is called ultra-weak bioluminescence, and it's distinct from the more dramatic light shows you see in fireflies or deep-sea creatures which derive from specialized chemical reactions. What's happening in your body is far quieter, far more subtle. It originates from routine chemical reactions occurring within your cells, primarily as a byproduct of oxidative stress, the natural processes where molecules in your cells react with oxygen. Occasionally the energy released from these reactions manifests as a photon, a tiny particle of light. And that photon, however weak, escapes. It travels outward, so you are glowing just faintly enough that specialized machines' incredibly sensitive cameras known as CCDs can capture it. Experiments, notably some conducted in Japan, have used these cameras to image people in completely dark, sealed rooms. And there it is, a subtle, shimmering glow. What's more, this glow isn't static. It varies throughout the day following a rhythmic pattern. It tends to be strongest in the afternoon and weakest late at night. It even subtly changes across different parts of the body, with the face often emitting a little more light than the rest. This variation suggests a deeper connection between our metabolism, our energy usage, and this low-level emission of light. But the truly remarkable thing is how little we understood about it for so long. For much of human history, we assumed we were dark creatures, that our bodies only reflected light, never emitted it. But our bodies are not entirely silent. Even in perfect darkness, there is a glow, a whisper of photons, an invisible announcement of life. It's not enough light to illuminate a room, not even close. But it serves as a profound reminder that even when you perceive nothing happening, when all is still an intricate dance of movement, chemistry, heat, and light is constantly unfolding within you. And this isn't just a curiosity. There's a tangible possibility, still speculative but very real, that this bioluminescence could have significant medical applications, because it's linked to oxidative processes involved in aging, disease and inflammation. Perhaps one day we could track a person's health by monitoring their glow. Not with the naked eye, of course, but with these ultra-sensitive systems acting like a biological candle, flickering brighter or dimmer depending on the subtle shifts occurring inside. So right now, as you sit there, your skin is quietly shining, a gentle, imperceptible luminescence, as if your cells are constantly invisibly announcing, "I'm alive." Sometimes I pause and think about the astonishingly small amount of energy the human brain actually uses. For everything it accomplishes, everything it's doing right now, as you listen, hearing, seeing, remembering, imagining, thinking, feeling, it's only burning about 20 watts. 20 watts. That's less power than a dim light bulb. It's almost comically inefficient, yet impossibly profound. You possess this 3-pound wrinkled lump of tissue not much larger than 2 clasped fists, and somehow, within that confined space, it constructs and runs your entire reality. Every thought you've ever had, every dream you've ever woven, every word you've ever spoken, every image you've ever conjured. All of it, every single bit, originates from that intricate electrochemical marvel. It's a symphony of neurons firing tiny electrical pulses, travelling down axons, chemicals, leaping across synaptic clefts. It's all just signals, just charges moving. But somehow miraculously it transforms into conscious experience. There are approximately 80, perhaps 86 billion neurons packed into that small volume, each one connected to thousands of others. The sheer number of possible connections, the potential pathways for information, is staggering, far exceeding the number of stars in our own galaxy. And each of those connections, each synapse, is not a fixed, rigid entity. It's dynamic plastic. It constantly strengthens or weakens depending on how often it's used. That's how you learn. That's how you remember. The very structure of your mind isn't static. It's a living, breathing landscape constantly moulded by your unique experiences. And yet, for all this astonishing complexity and dynamic activity, It operates on almost no energy. You cannot build a computer that efficient, not even close. The most powerful supercomputers we've engineered, massive machines the size of buildings, requiring elaborate cooling systems, with liquid nitrogen burning through megawatts of electricity, can simulate parts of a brain, but only parts and very slowly. Crucially, they still don't capture what it feels like to be aware. They don't possess consciousness. They don't wake up. You can feed them data, and they will process it with astounding speed, but they don't know anything in the way a human does. They don't experience the warmth of the sun or the sorrow of loss, which brings us to the profound mystery that no one not yet truly understands. How does mere electrical activity, how do chemical signals transform into a fully formed thought, into the vivid memory of your mother's face, or the tangible feeling of sunshine on your skin? That is the hard problem of consciousness, the really intractable one. We can scan the brain, we can meticulously map which regions illuminate when you speak, solve a puzzle or feel happy, but we still lack the bridge that connects that physical activity to subjective inner experience. The chasm between biology and awareness remains a profound enigma, yet somehow it happens. Right now, as these words reach your ears, your brain is decoding language, interpreting meaning, filtering sounds, even subtly, predicting what I might say next, all automatically, instantaneously. And you are largely unaware of most of this intricate work. You're only conscious of the top layer, the coherent thread of your thoughts. But beneath that, a vast unseen machine hums with activity tirelessly, keeping your heart beating your lungs, expanding your memories, arranging themselves quietly without any conscious instruction. So when you truly contemplate it, it's not that the brain is like a computer. It's that computers, even our most advanced ones, are mere crude imitations of the brain. The real thing, the one housed inside your skull, is still utterly unmatched in its efficiency, its complexity, and its capacity for consciousness. And it performs this miracle of existence with the modest power of a simple nightlight. It is perhaps the universe's most exquisite riddle etched in neural pathways. There's this idea, a truly radical one, that reality itself, the universe, everything we see and touch and move through, might not be quite what it seems. That our familiar three-dimensional world, complete with space-time objects and movement, could actually be a kind of projection, a grand cosmic hologram. I know. It sounds like something conjured late at night after indulging in too many science documentaries. But this concept astonishingly emerges directly from the frontiers of serious physics. Mathematics in certain contexts works. It began oddly enough with black holes and a deep paradox they presented. You see, when something falls into one of these incredibly dense collapsed objects, it appears as though all the information about that object simply disappears, irrevocably lost. And that is a monumental problem because in the fundamental laws of physics, particularly quantum mechanics, information is never supposed to be truly lost. It can be scrambled, hidden, transformed, but it cannot simply vanish from existence. So physicists began to grapple with this conundrum, attempting to understand the fate of information near a black hole. This quest led to a peculiar insight. They discovered that the total amount of information you can store inside a black hole doesn't scale with its volume, its interior, but rather with its surface area, its outer boundary, the event horizon. It's as if instead of the data being packed within the black hole, it's all meticulously written on its two-dimensional shell, like a vast cosmic code, much like a hologram projects a 3D image from a 2D surface. Then an audacious question arose: if this principle holds true for black holes, why not for the universe as a whole? Why not for everything? This led to the proposal of the holographic principle, which suggests that all the physics occurring within any given volume of space, everything happening in 3 dimensions, could be entirely described by data encoded on a 2-dimensional surface bounding that volume. The profound implication is that the 3-dimensional world we inhabit and move through is in a sense emergent. Not fake, not illusory in the sense of being unreal, but derivative. A deeper, more fundamental level of reality might reside in 2 dimensions, and what we perceive as our concrete 3D world is merely a projection of that underlying truth. And what's truly mind-bending is that this isn't just a philosophical flight of fancy. The holographic principle has found utility within advanced theoretical frameworks like string theory. It appears in complex calculations involving quantum gravity, and it even offers elegant solutions to certain problems in thermodynamics. It has become a powerful tool, a serious framework within modern theoretical physics, and it's making predictions that align with our observations. So it's no longer mere speculation. It has woven itself into the very machinery of how we try to understand the universe. And then you sit with it and you try to wrap your mind around it. The possibility that your hands, the solid floor beneath your feet, the vast open sky above might all be encoded somewhere else entirely. That the deepest description of reality might reside on an invisible boundary just out of our grasp. That your entire life might be written like lines on a page unfolding from a deeper hidden truth. And that truly does something profound to your sense of place in the universe. It shifts your perspective from being an inhabitant of a solid world to being a participant in a grand cosmic projection, a magnificent, intricate illusion. You know what's surprisingly easy to forget? That almost everything we perceive, all the glittering stars, the swirling planets, the vast gas clouds, the majestic galaxies, all of it comprises just a minuscule fraction of what actually exists in the universe, and I mean truly tiny. All the visible matter, the stuff that emits or reflects light that we can see or interact with accounts for only about 4, perhaps 5% of the universe's total contents. The rest, the overwhelming majority, is invisible. It's not invisible because it's too far away or merely dark in the conventional sense. It's invisible because it doesn't interact with light at all, not in any meaningful way that we currently understand. And yet it is undeniably there. It is profoundly affecting everything. Take dark matter, for example. It's called dark not because we know what it is, but precisely because we don't. We only know that something is out there, something possessing mass, something exerting gravitational pull, something that fundamentally holds galaxies together. If you observe how galaxies spin, how rapidly stars orbit their galactic centers, the standard mathematics based on visible matter simply doesn't add up. There isn't nearly enough visible mass to generate the immense gravitational pull required to keep those stars from flying off into space. Galaxies should by all rights be flung apart, but they don't. They remain cohesive, spinning too fast yet holding together with an invisible glue. The only viable explanation we have so far is the presence of this other invisible stuff, dark matter, creating the extra gravity. It acts like a cosmic scaffolding, an unseen architectural framework made of, well, we don't know what. We've tirelessly tried to detect it, directly building elaborate experiments in deep underground detectors, hoping that just one elusive particle of dark matter might bump into something we can see. So far, nothing definitive, yet its gravitational effects are consistent, undeniable, and pervasive. It's not just in galaxies. Dark matter fundamentally shapes the structure of the universe itself, forming vast, intricate webs of giant galaxy clusters, stretching across millions of light years interspersed with immense voids. The entire large-scale arrangement of the cosmos is as if something unseen is subtly pulling the strings, dictating the dance of galaxies. And then just when that concept begins to settle in its strangeness, there is dark energy. That's even weirder. In the late 1990s, astronomers made an astonishing discovery that no one had anticipated. They were diligently measuring how fast the universe was expanding, and the logical expectation was that this expansion should be slowing down. After all, gravity pulls things together, right? Over vast cosmic timescales, expansion should decelerate. But instead, they found the opposite. The expansion was speeding up. Space itself was stretching faster and faster. And once again, we have no idea why. So we gave it a name, dark energy. But it is in essence merely a label for something utterly unknown, a placeholder for a cosmic force we cannot comprehend. It accounts for an astounding 68% of the universe, nearly 70%, and we still lack any fundamental understanding of its nature. It could be the inherent energy of the quantum vacuum or something far more exotic, a dynamic, ever-changing field. We simply don't know. but it is undeniably real. Its effects are measurable, driving the grand cosmic acceleration. So when you gaze up at the night sky at the familiar glow of stars, remember this: you're only seeing the surface, the visible tip of an unimaginably vast iceberg. Everything else, the overwhelming majority of the cosmos, remains hidden, unseen, yet profoundly shaping the universe all the same. It's like shadows with immense mass, like an emptiness that actively pushes silently, orchestrating the grandest symphony of all. Our visible universe is merely a thin, luminous veneer on a profound, energetic mystery. There's this experiment, a truly famous one actually, the double-slit experiment. It's the kind of thing you might encounter in a textbook and perhaps quickly move past thinking it's just another fundamental concept. But the more you truly delve into its implications, the more it fundamentally messes with your perception of reality. Because it doesn't just suggest, it demonstrates that particles like electrons can exist in more than one place at once. Not metaphorically, not poetically, but physically, literally. Imagine you fire a single electron at a barrier that has two narrow slits cut into it. Just one electron at a time, not a stream, but a lone particle. You repeat this process, sending individual electrons one after another over and over again. What you expect to see on the screen behind the barrier are two distinct bands corresponding to the electrons passing through either the left or the right slit. But what you actually get is an interference pattern, the same kind of ripple pattern you'd see if waves, like water waves or light waves, passed through both slits simultaneously and interfered with each other, but you are sending individual particles. How can a single electron interfere with itself? It suggests that the electron, when unobserved, behaves like a wave, not just an ordinary wave, but a wave of probability, a spread out cloud of all the possible locations it might occupy, all the paths it could explore. And it seems to traverse both slits at once, interfering with its own possibilities, exploring every potential trajectory simultaneously. That is, until you try to measure it. And that's the truly bizarre part. The moment you attempt to observe which slit the electron passes through, the interference pattern instantly vanishes. The electron ceases to behave like a diffuse wave and abruptly acts like a definite particle again. The very act of observation of measurement somehow collapses the wave function. It forces the electron to choose a single path. It's as if the universe holds all its options open, doesn't commit to a single outcome until it's looked upon. And this is not just poetic language. This is the core of quantum mechanics. This profound idea that things can exist in multiple states simultaneously is called superposition. And it's not limited to electrons. It applies to atoms, even to small molecules. The larger the object, the more fragile and fleeting the effect becomes, making it incredibly difficult to observe in macroscopic objects. But in principle, it applies to everything, including you, including me. At the quantum level, reality isn't a collection of solid, definite things. It's a blur, a smudge of overlapping possibilities. It's only when a measurement occurs, only when an interaction forces a choice, that things settle into a fixed state. This leads to all sorts of strange interpretations. Is the observer somehow special? Is consciousness required to collapse the wave function? Most physicists would argue no. Any interaction, even with a mere detector, seems sufficient. But still, the perplexing fact remains. Reality behaves fundamentally differently depending on whether or not it is being watched or interacted with. It's as if nature keeps her options open right up until the last possible second. And this principle of superposition isn't just an abstract philosophical curiosity, it's the very basis of quantum computing. In classical computing, a bit is either a 0 or a 1, but in a quantum system, a quantum bit qubit can be both the 0 and 1, simultaneously existing in a superposition of states. This allows for massively parallel computations, promising exponential increases in processing power that could revolutionize technology, medicine, and our understanding of complex systems. It's still early days, but if this technology scales, it could transform everything. Yet underneath all of its potential, there remains this strange, inescapable truth. The world at its most fundamental level isn't made of solid, definite objects. It's made of probabilities of possibilities. And until something pushes the system one way or the other, everything that could happen is in some profound sense already happening. It's a universe of quiet potential, waiting for its story to be told by interaction. There's this idea that seems at first glance utterly obvious, almost too simple to question. It's the notion that time flows universally the same for everyone, ticking at an identical rate everywhere, that a second for you is precisely a second for me, regardless of where we are or what we're doing. But this comforting intuition, it turns out, is not how the universe works. Time isn't universal. It's deeply personal, wonderfully relative. And here's the truly strange part: you can actually measure the difference. Imagine this scenario. You take two incredibly precise clocks, atomic clocks, the most accurate timekeeping devices humanity has ever built. You place one of them at sea level, and the other you carefully transport it up a mountain, not even a dramatically tall one, just a few thousand meters above the first. You let them run perhaps for a day or a week, and then you compare their readings. What you will discover is that they have drifted apart ever so slightly. The clock on the mountain has ticked ahead. It has experienced marginally more time simply because it was farther from the Earth's centre, experiencing a fractionally weaker gravitational pull. The difference is minuscule, measured in nanoseconds, sometimes even less, but it is unequivocally real. It's not an error in measurement, it's not a glitch in the clocks. It is a fundamental property woven into the very fabric of space-time. General relativity tells us that the closer you are to a massive object, the slower time passes for you. Gravity isn't merely a force pulling things down, it is a curvature of space-time itself. Mass bends this cosmic fabric, and time itself flows differently within that curved geometry. So if you live on the ground floor of a towering building, technically you're aging a tiny bit more slowly than someone who resides on the very top floor, simply by virtue of being closer to the Earth's gravitational centre. And this isn't just a theoretical curiosity for physicists to ponder, it's something we must correct for constantly. GPS satellites, for example, orbit high above the Earth. They experience two opposing relativistic effects. Their high speed causes their clocks to slow down due to special relativity, but their greater distance from Earth's gravity causes their clocks to speed up. Both effects must be precisely accounted for. If we fail to do that, if we simply allowed those satellites to tick away uncorrected, your location on a map would drift by kilometers every single day. You would never find your way. So every second you experience is a profoundly local thing unique to your position and velocity. Even between you and someone sitting right next to you, there exists a tiny, imperceptible difference in how fast time is passing. And the greater the difference in gravitational pull or relative velocity, the more pronounced the effect becomes. If you were to fly close to the speed of light or orbit perilously near a black hole, you could experience hours while years, even centuries passed for someone else back on Earth. That is not a paradox, that is simply how time works in our universe. So when you ask, what time is it? The answer is far more complex than we ever imagined. Because there isn't one time. There's your time and there's my time, and they are never ever quite the same. It makes our shared experience of now a magnificent fleeting convergence of personal timelines. You know, one of the things that consistently surprises people, and it should surprise you because it's profoundly counterintuitive, is the notion that you've never actually touched anything. Not truly. Not in the way we instinctively believe we do. Think about it. You sit down in a chair, you shake someone's hand, you press your finger against a solid table. We call that contact. But what's actually happening isn't a fusion of matter, no real meeting or merging of surfaces. What's really at play is something more akin to repulsion. Forces are pushing back. It's an electromagnetic dance. At the atomic level, atoms themselves are mostly empty space. Another bizarre truth, but let's set that aside for a moment. The outermost layer of an atom is where the electrons reside, existing not in neat orbits, but in diffuse clouds regions of probability. And electrons possess a negative electrical charge. So when you bring one atom close to another, their electron clouds vigorously repel each other. Because like charges do that, they push away with immense force. Thus, when you sit in a chair, your atoms don't actually merge with the atoms of the chair. What's occurring is that the electrons in your body are being pushed back by the electrons in the chair. There's an invisible cushion, a powerful electric field that relentlessly keeps the particles from overlapping. And that repulsion, that invisible energetic push, that is what you feel. That is the pressure, the resistance, the sensation of solidity. You are in essence floating just infinitesimally above the surface of everything you perceive to be touching. Even the sensation of touch itself, the very feeling of it, isn't due to direct physical contact. It's your nervous system responding to these electromagnetic forces. It's interpreting this resistance, this invisible pushback, and converting that raw data into the complex experience we call touch. So when you press your hand against something and declare, "I'm touching it," what you're truly saying is, "I am feeling the force that prevents me from going through it." And if that weren't strange enough, quantum mechanics takes it even further. There's a fundamental principle called the Pauli exclusion principle. It states that no two identical fermions, a class of particles that includes electrons, can occupy the exact same quantum state at the same time. And this principle is a foundational reason why matter has structure, why atoms don't simply collapse in on themselves. It's not just repulsion, it's a deep intrinsic rule woven into the fabric of the universe that effectively says, you cannot be here because someone else already is. It's why electrons arrange themselves in distinct shells around atomic nuclei. It's why matter doesn't implode under pressure. It's why, in a profound sense, you don't fall right through the floor. So when you contemplate what we call solid objects, you're not actually envisioning something truly solid in the intuitive sense of packed matter. You're envisioning intricate interactions between fields, between probability distributions fiercely resisting compression. It's forces, not contact. Fields, not surfaces. And all the while, nothing is ever truly fundamentally touching anything else. It's a grand subatomic dance of proximity, a breathtaking choreography of repulsion. And you are suspended within that vast invisible field of interactions, always just a little bit above the world, held there by invisible energetic hands. It reminds us that our sensory world is a magnificent interpretation, not a literal mirror of the quantum reality beneath. It's strange really how we perceive things as being solid, as being full. Like objects are these dense, tangible, impenetrable things. A chair, a book, your own body. But when you delve down to the fundamental scale of atoms, it turns out they are mostly nothing. And I don't mean a bit of space between things. I mean mostly almost entirely empty. It's a concept profoundly difficult to grasp, because what we term matter, what we think of as the fundamental stuff of the universe, is actually composed of tiny particles suspended in a vast, unimaginable openness. Let's take a single atom. At its core, it has a nucleus, an incredibly tiny, incredibly dense centre, made of protons and neutrons. And then there are electrons, which don't orbit like planets around a sun that's an outdated though helpful image. Instead, they exist in probabilistic clouds smeared out around the nucleus, their exact position a blur of potential. But the scale of it, that's the truly astonishing part. If the nucleus of an atom were the size of a peanut, the electron cloud, the region where the electrons might be found, would stretch out over an entire football stadium. That's the kind of ratio we're talking about. And in between that peanut-sized nucleus and the stadium-sized electron cloud, nothing. Just pure vacuum, pure empty space. It's not as if the particles are packed tightly together. They're not even close. They're more like isolated islands, infinitesimally small, floating in a vast, invisible ocean of nothingness. The mass of the atom is almost entirely concentrated in that tiny nucleus, but the volume, the space it occupies, is overwhelmingly defined by its emptiness. So when you hold something in your hand, what you're actually holding, what you're actually touching, or rather repelling, is mostly space-structured space. Certainly space-threaded with electric and quantum forces, but space nonetheless. And this principle applies not just to individual atoms, but to molecules, to cells, even to entire macroscopic objects. They're all built upon this same astonishing architecture layers of profound emptiness, meticulously held together by intricate interactions. The very idea of solidity, then, is truly an illusion, a powerful perception generated by fundamental forces. What you feel as solid is the fierce resistance of these invisible fields, electromagnetic forces keeping atoms in their relative positions and quantum rules like the Pauli exclusion principle, preventing particles from overlapping. But the stuff itself, the underlying matter, it's not densely packed in the way our senses imagine it. Even the nucleus, which appears incredibly dense, is itself made of particles, quarks, gluons, that might not be fundamental, swirling around in their own internal void. And if you dig even deeper, there's string theory, which proposes that perhaps underneath it all particles aren't even point-like objects. They're instead tiny, vibrating loops of energy like infinitesimal strings. And if that's true, then everything, literally everything, is made of oscillations in empty space, nothingness vibrating into existence. So when you gaze at your hand or a stone or a distant star, you're looking at something that is barely there. Yet because that emptiness is so exquisitely organised, because it's patterned and shaped by laws that have held since the very beginning of time, it behaves like a thing, like an object, like solid matter. But at its heart it is void, and we somehow are made from structure built out of nothing. Which means that in a very real and humbling sense, the universe is not full of things. It's full of almost things, whispers of presence held together by absence, a symphony of void. There's something both unsettling and magnificent about contemplating the fate of our sun. Not today, not in our lifetimes, but in the deep future, billions of years from now. Our sun, like all stars, has a life cycle. It is born, it burns, and one day it will die. Right now, it lives in perfect balance, hydrogen fusing into helium in its core, light pushing outward, while gravity pulls inward. But this harmony is temporary. When the hydrogen runs out, that balance will shatter. The core will collapse under its own weight, heating the surrounding layers until new shells of fusion ignite. The sun will swell into a vast red giant, engulfing Mercury, Venus, and perhaps even Earth. Long before that, our oceans will boil away, the atmosphere will vanish, and the surface will melt into a glowing sea of stone. This isn't speculation, it's physics. A star like ours must change. In its final phase, the sun will expand to hundreds of times its current size, its light turning red and dimmer, yet vastly more luminous. Life in any recognizable form will end not in an instant, but over millions of years of slow, relentless transformation. The star that gave us everything will in the end take it all back. And still there is beauty in this destiny. The sun's death is not destruction, it's release. Its outer layers will drift away, forming a delicate planetary nebula, a cosmic blossom fading into the dark. What remains will be the sun's exposed core, a white dwarf small as Earth, but half as massive as the sun itself. No fusion, no new light, only a silent ember glowing for billions of years before cooling into darkness. We live in the sun's brief golden moment, a narrow window between its birth and its quiet extinction. Each photon that warms our skin is part of its countdown. Someday, far beyond us, that light will fade forever. A reminder that everything, even the source of life itself, is temporary. But stars die in many ways. Some collapse far more violently, ending not in quiet embers, but in explosions that reshape the cosmos. When a star much larger than our sun reaches its end, gravity crushes it until protons and electrons fuse into neutrons. The result is a neutron star, a sphere no larger than a city, yet more massive than the sun. If you could scoop a single teaspoon of that matter, it would weigh billions of tons more than a mountain. Inside there are no atoms, no empty spaces, just an ocean of neutrons packed tighter than imagination allows. These stars can spin hundreds of times per second, emitting perfect beams of radiation, like cosmic lighthouses, pulsars so precise that we use them as galactic clocks. It's a breathtaking equilibrium gravity trying to crush everything into oblivion, and the strange quantum forces of matter, pushing back just enough to hold. One step further and the star becomes something darker still, a black hole where not even light can escape. And beyond all this, beyond the death of stars and the fading of light, there may come an end so complete that even atoms cannot survive. Cosmologists call it the Big Rip, a final unimaginable unmaking of the universe itself. We already know the universe is expanding, but what if the mysterious dark energy driving that expansion isn't constant? What if over time it grows stronger faster, tearing apart not just galaxies but the very fabric of space? At first galaxies would drift apart, then the stars within them, then planets from their suns, then atoms from atoms. In the final moment, space itself would rupture. Time would lose meaning. Everything, matter, energy, even the laws of physics would dissolve into an accelerating void. This is only one possibility. Perhaps the expansion will slow or end in quiet heat death. Perhaps something else entirely awaits us. But the Big Rip, whether real or not, reminds us of a deeper truth we live inside equations still unfolding. The laws of the cosmos are not done writing their story. We are born from the fires of stars, living for a blink beneath a temporary sun, in a universe that might one day rip itself apart. Yet in this fragile instant between beginnings and endings, there is awareness us. Consciousness looking back at the stars that made it, realizing for just a moment the astonishing fact of being. And maybe that is enough. Sometimes I try just for a moment to picture it, to grasp how much is really out there. And every time the mind slips, the scale is too vast, too strange. Yet there's one comparison that almost makes sense. There are more stars in the observable universe than grains of sand on all the beaches of Earth. Every coastline, every desert, every handful of sand you've ever seen outnumbered by stars. Each of those stars could be a sun, some wrapped in dust and gas, some orbited by planets, maybe even by life, wondering as we do who else might be watching the same sky. Our galaxy alone, the Milky Way, holds perhaps 200 billion stars. And there are hundreds of billions of galaxies, each one an island of suns adrift in an ocean of darkness. For most of human history, we believe the sky held only a few thousand lights. Then came telescopes, then came Hubble, and the image that changed everything, the Hubble Deep Field. Astronomers pointed it at what looked like empty space, a patch no bigger than a grain of sand held at arm's length. What they found were not stars but galaxies, thousands of them, each containing billions of suns. And that's just the part of the universe we can see. Beyond it, space continues perhaps infinitely. The light from distant realms simply hasn't reached us yet. So when you look up, remember, you're not seeing the universe as it is, but as it was billions of years ago. The night sky is a memory of fire. It's humbling to realize how small we are, a single world circling a single star inside one spiral arm of one ordinary galaxy. And yet from this tiny speck we have begun to map the cosmos, to send our questions into the dark, to wonder whether someone somewhere is asking the same questions back. But what if our universe is not alone? What if everything is only one chapter in a much larger book? Cosmologists call it the multiverse, a grand ensemble of universes, each with its own laws of physics, its own beginning, perhaps its own version of you. The idea began with cosmic inflation that in the first instant after the Big Bang space expanded faster than light itself. But that expansion may not have stopped everywhere. In some models, it ends only in patches, bubbles. One of those bubbles became our universe. Elsewhere, inflation continues, birthing new universes endlessly, like foam on a cosmic sea. Each bubble sealed off from the others, unreachable, yet real. And then there's the quantum view. At the smallest scale, particles don't choose a single state until they're observed. They exist in many possibilities at once, a concept called superposition. The many worlds interpretation says every possible outcome actually happens, each in its own branching universe. Every decision, every random event splits reality into countless paths. In some branch you turned left instead of right. In another, you never existed at all. We may never detect these other worlds. Their light will never reach us. But the mathematics allows them. And so the possibility lingers a reminder that reality could be far larger, far stranger than anything our senses can confirm. And within this boundless cosmos, amid all these possible worlds, something even more mysterious arises, thought. Consciousness. You. Ask yourself, what is a thought? Where does it begin? Whatever the answer it is. Electrical. Your brain is a storm of pulses, billions of neurons firing in delicate patterns, exchanging tiny surges of voltage. Each firing produces an electric field so faint it barely exists, yet together they form a rhythm, a hum that can be measured. That hum is your mind thinking. Electroencephalograms record these rhythms, delta, theta, alpha, beta waves that shift as you sleep, focus, or dream. They are not random noise. They are signatures of awareness, proof that thought itself rides upon electricity. And sometimes vast regions of the brain begin to synchronize neurons firing together in perfect resonance. That harmony allows memory, attention, and the fragile miracle of self-awareness. When it falters, consciousness fades. Under anesthesia or in deep illness, the rhythm breaks, and the light of awareness flickers out. So in a sense, your mind is an electromagnetic song, rising and falling in the silence of your skull. You're not apart from the universe, you're one of its patterns, an organized shimmer of energy, in an ocean of space and time. The same forces that forge stars now pulse through the circuits of your thoughts. Somewhere out there in the vastness beyond measure, galaxies collide, and new worlds are born. Somewhere else, other minds may awaken, shaped by their own laws built from the same cosmic dust. And here you are, one consciousness briefly aware of it all. The universe is immeasurable, perhaps infinite. But the fact that you can stand beneath it and wonder that you can think about thinking as its greatest miracle, we still don't truly understand how it happens, how billions of tiny electrical sparks inside your head become a thought, a memory, or the feeling of being alive. We can map brain circuits, trace every signal, but the leap from voltage to experience the smell of rain, the memory of childhood, the awareness of I am remains a mystery. Whatever the mechanism, it is electromagnetic. Your thoughts are fields. Your emotions are patterns of firing. You are quite literally a storm, an intricate, organized storm of electricity contained within bone. When that storm ends, the mind ends. The field fades, the signal stops, and what remains is only silence. It's humbling, realizing how fragile yet magnificent this electrical symphony of consciousness truly is. And to think it all began with one cell, a single microscopic sphere smaller than a grain of salt, carrying the complete blueprint for everything you are, limbs, eyes, memories, the potential to love and question. That cell formed when two others met, divided again, and again, not chaotically, but with purpose. Some cells became skin, others bone, others neurons, all reading different lines from the same book of DNA, as if following an unseen conductor. This is called differentiation, a chemical ballet of signals and timing. From it, a spine folds, a heart beats, a brain sparks. At certain stages, your tiny form even carried gill slits, and a tail echoes of distant ancestors. Because evolution doesn't erase, it rewrites. Deep within you are traces of earlier worlds, proof that life builds itself from what came before. From that single cell emerged consciousness of being able to look back and ask how it began. No divine sculptor needed, just physics and chemistry playing out their patient dance. You are the universe learning to think. And what a universe it is. Everything in you, the carbon in your cells, the calcium in your bones, the iron in your blood, was born in the hearts of ancient stars. In the beginning, there was only hydrogen and helium, the simplest elements. But inside stars, under unimaginable heat, those atoms fused, becoming carbon, oxygen, and beyond. When massive stars exhausted their fuel, they collapsed and exploded supernova that scattered new elements across light years. Gold, copper, zinc, all born in that violent breath. Over eons, that stardust gathered again, forming new stars, new planets, and on one small world, you. The iron in your blood once glowed in a star's core. The oxygen you breathe was forged in its fire. When we say we are made of stardust, it's not a metaphor, it's physics. You are the universe recycled atoms that burned, drifted, and reassembled into something that can wonder about itself. The cosmos is not out there. It's in you, thinking through you. And even time, the very stage on which this story unfolds, had a beginning. We like to imagine time as an endless line stretching forever backward, but it wasn't. The universe didn't begin inside space. It brought space and time into existence. The Big Bang wasn't an explosion in emptiness. It was the birth of the fabric of reality itself. Before that moment, there was no before. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question dissolves. Time itself began there, emerging as the universe expanded and cooled. Every galaxy, every life, every thought has unfolded within that single shared timeline. It's unsettling, yes, but also profound. Because it means everything from the birth of the stars to the firing of your neurons belongs to the same story. The same unfolding of space matter and energy that began when time began. You're made of ancient light sculpted by physics, animated by electricity and sustained by atoms, born billions of years before Earth existed. You're a continuation of the first spark, a ripple in the grand pattern that began when the universe itself opened its eyes. And perhaps when your own electrical storm finally fades, it won't truly vanish. The atoms will remain drifting again into the cosmos, ready to become something else. Another flame, another thought, another being who will look up at the stars and wonder where they came from. Because in the deeper sense, you're not separate from the universe. You're the universe briefly aware of itself. If time had a beginning, it might also have an end. Physicists have proposed several possibilities for how that might happen. The most widely accepted is the heat death of the universe. In this scenario, the cosmos expands forever. Energy thins, stars die, black holes evaporate, even matter itself decays. Eventually all motion ceases. No light, no warmth, no difference, just a cold uniform silence. And if nothing ever changes again, can time still exist? Time is not an independent river. It's the measure of change. Without change, perhaps even time itself stops. Other endings have been imagined. The Big Crunch, where expansion reverses and everything collapses back into a single point. Or the Big Rip, where dark energy grows stronger until it tears apart galaxies, atoms, and finally space-time itself. Different paths, same truth. Time is not infinite. It has rules, boundaries, a beginning and an end. And here we are, right in the middle of that story. Between the birth of time and its eventual silence. A thin, brilliant sliver of existence where stars still shine, where complexity can bloom, where consciousness can ask questions. Your time. The seconds you live right now is carved from this narrow window between nothing and nothing. In the grand cosmic quiet, you're a brief flicker of awareness, but time itself is stranger than it appears. Relativity tells us that now is not universal. There is no single cosmic moment that everyone shares. Imagine you here on Earth and someone light years away. You'd assume there's one shared present, one instant that unites you. But physics says otherwise. Simultaneity is relative. Move even slightly and your slice of the present shifts. What is now for you could be the distant past or future for someone else. Each observer carries their own timeline, their own version of reality. Once you accept that time stops feeling like a flowing river, it becomes a vast frozen landscape, a block universe as physicists call it, where the past, present and future already exist together like pages in a completed book. We don't watch time pass, we move through it. Or perhaps we simply are existing as fixed coordinates in a four-dimensional whole. It's unsettling but beautiful. It means nothing is truly lost. Every instant, your first breath, your last thought still exists somewhere within that timeless geometry. Your sense of now is just your own slice of that infinite structure. Someone else's now cuts through it differently, and both are real. And within this strange framework of time, another question arises. What does it mean for something to be identical? In the 20th century, physicist John Wheeler proposed an idea so wild it still echoes through theoretical physics. What if every electron in the universe is actually the same electron? Not merely identical, but literally one particle looping forward and backward through time, appearing in countless places and moments. It sounds absurd, but consider this. Every electron ever measured has exactly the same charge, the same mass, the same properties. Not approximately exactly. No variation anywhere ever. Why, Wheeler wondered if it was because they are all the same entity weaving through space-time in an endless zigzag. When it moves forward, we call it an electron, backward a positron. The universe then might be stitched together by a single particle, tracing one immense eternal path. This one electron universe isn't accepted literally, but it points towards something profound. At the quantum level, individuality dissolves. Two electrons can be swapped, and the universe remains identical. There are no labels, no identities, no this one or that one. Particles of the same kind are not merely similar, they are indistinguishable in principle. And that indistinguishability is what gives matter its structure. The Pauli exclusion principle, the rule that no two identical fermions can share the same quantum state, is why atoms hold their shape, why matter is solid, why chemistry and life can exist at all. Without this strange sameness, the universe would collapse into featureless energy. So Wheeler's idea, however, speculative hints at a deeper unity. Maybe the universe is not made of countless separate things, but of recurring patterns, echoes of one fundamental process expressing itself in endless forms. Perhaps there aren't many electrons, but one way of being an electron repeated everywhere. When you follow that thought to its end, individuality itself becomes relative. Every atom in your body follows the same laws as the atoms in a distant star. Every field, every vibration part of the same underlying rhythm, and then the boundary between you and everything else begins to blur. You, the observer, are not outside the universe. You're inside it, made of it, moving through its time. The same particles that build the stars also build your neurons. The same rules that shape galaxies shape your thoughts. You're not separate from the cosmos, you're one of its patterns, briefly self-aware. So when you look up at the stars, you are in a very literal sense looking at your own origins, at the atoms that once were light, now thinking about themselves. You are the universe's way of observing its own unfolding, a flicker of consciousness suspended in the vast timeless geometry of space-time. And though your moments will pass, though the great clock of the cosmos will one day stop, your existence is still part of that eternal structure woven into the fabric of all that has been and all that ever will be. You're not outside the story. You're the story written in starlight, measured in seconds and carried along the invisible thread of time,